Okay, so thank you everyone for being here. So what I'm speaking about, you see from the title, is a strange topic in the sense that it deals with distortions. So I will define what I mean with distortion and the appearance and the use of these distortions in finance. So if you are here because you think of the distortion of finance as something that is sociopolitical, this is not the case. So I'm not criticizing capitalism or stuff like that. It's really from the mathematical point of view. This is a joint work with different friends. So Peter Carr from NYU, Jürg Hüssler from the University of Bern, and Andrea Fontanari, who is my PhD student. Actually, I would say former PhD student because he's just finished. So now he's in Eindhoven in the Netherlands. Okay, so let's try to see what is a distortion. So what do we mean when we say distortion? Now, a distortion function, it's a very simple object. So it's a function that maps from the unit interval to the unit interval, and it has very basic characteristics. In 0, it is 0. In 1, it is 1. And it is non-decreasing. Okay? So it will increase or it will be constant, but it will never decrease. So it is an object of this type. So it starts in 0, ends in 1, and it can be convex, concave, a line. That's what we call a distortion function. Now, why are these objects useful? Because these objects can be used, despite their apparent simplicity, to generate probability measures, to distort probability measures starting from another probability measure. They can be used to build risk measures that are called distorted risk measures. And you will for sure know some of them. Now, in order to create a distortion probability measure or a distorted probability measure, what do? You start from a probability space in which I have a probability measure P. So I have my measurable space on which I have my probability measure P. And I can define a new probability measure Q of V, which is nothing more G, the distortion function, applied to the probability that P assigns to the event E. Since G maps from 0, 1 to 0, 1, and a probability by definition is between 0 and 1, it can be the argument of a distortion function. Now, what is quite easy to verify is that if I define this new probability measure in this way, P and Q are equivalent. What do I mean with equivalent? P and Q will always agree on those sets, on those events that are not possible. So if you want to be particularly, let's say, formalized, you would say that they agree on the sets of measure 0. Okay? Prosaically speaking, is just to say that if something is not possible, so it has a probability 0 on the P, it will have probability 0 on the Q, and vice versa. Okay? A distortion risk measure is then defined in this way. I consider, so I take the risk management point of view. Now, there is a specific difference between, for example, asset pricing and risk management. When you are investing, when you have the returns on your portfolio, we are all used to think that positive quantities are the returns and negative quantities are the losses. In risk management, you flip. Losses are the positive things, the returns are the negative losses. Okay? But it's just a convention. So I take X to be a non-negative random variable. Why non-negative? Because if I'm a risk manager, essentially, I'm just interested in the losses, not in profits. This is for other departments to be cheerful about, not for me. I'm a sad guy. I just look at losses. So I take a non-negative random variable with a given CDF, cumulative distribution function f, and what I call the survival function, which is nothing more than 1 minus. So f is the probability that my random variable x is smaller than or equal to something. S is just the probability of being above something. Okay? If I do that, I can define a distortion risk measure rho, which is obviously depending on the function g that I'm using, which is nothing more than the expectation under the measure q, which is this measure here, of x. If you want to just represent that in terms of an integral, it's nothing more than the integral between 0 and plus infinity, because x is not negative, of g applied to the survival function. Why? Because we know that the expectation of a random variable can be represented as the integral of the survival function, and here we are just distorting that object. That is what we call a distortion or distorted risk measure. Now, given this definition, essentially, we can already say a lot of things without even entering into examples. Just making hypotheses on g. You remember, I'm just requiring g to be 0 in 0, 1 in 1, non-decreasing. But now I can specify. So for example, I can assume that g is convex or g is concave. So it's convex, the second derivative is positive, or concave, the second derivative is negative. If I do that, what can I see? I see that if g is concave, then the risk measure I'm generating is coherent. If g is convex, it is not coherent. What do I mean with coherent? I don't know if you already covered that in your courses, but for sure you will do that in risk management. A coherent risk measure is a measure that possesses 4 main properties. It is monotonic. It means that if I think that something is riskier than something else, then the risk measure assigns a higher risk to that, and higher risk, the risk measure is nothing more than the element that you use to quantify the capital that you have to put aside to hedge a given risk. Okay? So if I have a monotone risk measure and I think that an event is riskier than the other, obviously I will put more capital aside to hedge it. So it's a trivial requirement. The other one is translation invariance. What does it mean? It means that if I have a portfolio that has some risk and I add a risk-free asset, like for example cash, obviously the total risk of the portfolio does not increase. Okay? Simple as that. In some specification, actually you can even think that the total risk decreases. Why? Because you can already see cash as a capital that you are putting in the portfolio. But these are minor things. Then we have positive homogeneity of order 1. It means that if I have a portfolio and I double the portfolio in all its components, I'm doubling the risk. And finally, subadditivity. If I can diversify my portfolio, the risk measure will tell me that it's good to diversify. So the total risk decreases if I diversify. These are the properties that we require for a measure to be coherent. In risk management, you will see that the value at risk is not a coherent risk measure. The expected shortfall is a coherent risk measure. And then there is a lot of discussion. It is better to use one, the other. We don't care. Just to tell you that depending on the properties of G, we can actually already say something about the risk measure that we are generating. So let's consider just 2 very simple examples. I can, for example, define this function g, which is equal to 0 if the argument is between 0 and 1 minus alpha, and is equal to 1 if the argument is between 1 minus alpha and 1. If you do that, and you apply this definition here, it is not very complicated to show that you are defining the value at risk. So the value at risk can be represented as a distortion risk measure. And since you can immediately see that here we are not essentially defined in a proper sense concave function, is not coherent. If you want the expected shortfall, you just change the function. Okay? Just to show you that the class of distortion risk measure is essentially quite rich, and it includes most of the risk measures you can think of. Most. Not all, but a great part. Okay. Now, for a moment, put distortion function, distortion risk measures, and distortions and friends aside. And let's introduce a second object. This second object is something that comes from a very specific field of statistics, which is called inequality studies. So it's totally non-financial in a sense. It's like the field of statistics that deals with the questions like, I have the distribution of income or of wealth in one economy, like the US, like Italy, like the Netherlands, like India, like China, like Japan, like Australia, wherever you want. I know what is the income of the different individuals, and I want to know how equal or unequal the economy is. That is to say, if there is a lot of difference between the rich guys and the poor guys, less difference. If it is a totally fair society in which everyone has the same amount of money, there is very big difference. So I can study that from a statistical point of view. And there are different tools. These tools are many, but for us, just two of them are very important. One is called the Lorenz curve, and one is called the Gini index. Now, the Lorenz curve was introduced in 1905 by Max Otto Lorenz, and the Gini index was introduced in 1912 by Corrado Gini. These two objects are very simple. The intuition is very simple, and it's the following. Imagine for a second that I'm just interested in the wealth of people, okay? And I want to know how this wealth is spread, is shared in the economy. Now, if I had the wealth of every single individual, I just take the sum, and that's the total wealth of the economy, okay? Very simple. And then what do? I order the individuals in the economy from the poorest to the richest. And then I ask myself the question, if I take the first 10% of the population, what's the share of the total wealth they own? Or if I take half of the population, which is the amount of the total wealth they own? You probably heard of the 80-20 principle in the Pareto distribution, in which you say that, for example, 20% of the population accounts for 80% of the total wealth. Okay, that's the typical example. The Lorenz curve is an object, a curve, that essentially tells you that if you're able to compute the Lorenz curve of a random variable, that would be non-negative, because obviously it's either the income or the wealth, and we assume that we don't have negative wealth and negative income. Actually, we can have it, but we ignore that. What you have? You have that here you can read the percentage of the population, and here the percentage of the total wealth they possess. Okay, so the Lorenz curve tells me that if I take this percentage of the population, this is the share of the total wealth they own. Okay? Now, the Lorenz curve is, by definition, between two important boundaries. One boundary is called the PE, the perfect equality Lorenz curve, which is the specific case in which every single individual in the economy has the same amount of wealth. Okay? So it's like here we have $1 million and we split among us the same amount among us. The opposite situation is the situation in which there is $1 million in the classroom, but only Professor Shimko has it. In that situation, we are in the so-called perfect inequality case, which is exactly this line. It is 0 for everyone apart from one guy that jumps to 1. Okay? So the total wealth is in the hands of just one guy. And the Lorenz curve, you can prove it, is mathematically between this line and this line. Okay? Given a Lorenz curve, and then I will give you the formal definition, but assume that for the moment we just know that this is the curve, I can measure the area between the perfect equality and the Lorenz curve, this green area, okay? This green area that I called A, if I multiply this area by 2, I can compute G. G is the Gini index. The Gini index is a synthetic measure, is a summary measure of the Lorenz curve. The Lorenz curve is a curve, so you have an infinity of points. If you assume that it is continuous, the Gini index is just one number out of that. Gini is between 0 and 1. Why? Because if the Lorenz curve corresponds to perfect equality, then the area is 0. If the Lorenz curve corresponds to the perfect inequality, this area, which is the lower part of the unit square, is just 1/2. Okay? Multiplied by 2, 1. 0, it's perfect equality in the economy. 1, perfect inequality in the economy. Okay? That's the Gini index. Another representation that you can have, and maybe it's why you can understand why we take 2, is the following. This is A, okay? This is B, call this area here B. Then Gini can be represented as A over A plus B. But since A plus B is 1/2, it's A divided 1/2, so 2 times A. Okay, that's the graphical representation. Let's see how we can mathematically define these objects. So for the Lorenz curve, it's very simple. I have a non-negative random variable, again, because I'm thinking about wealth or income or losses. So just non-negative with a specific CDF. So the distribution is ELF. The only strict requirement that I have, so for example, these objects can be used in extremely fat-tailed situations. It's not important to assume normality. It's not important to assume anything. The only thing that you have to assume is that your random variable has a finite mean, which is not a very strong assumption, okay? Why a finite mean? Because we divide by that, okay? So we want that to be a finite number. Given that assumption, we can define the quantile function, which is nothing more than the inverse, or the generalized inverse, if you have discontinuity points, of the distribution. Okay, that's the quantile function. It's the function that, to a given probability, gives me the value of the corresponding x, such that the probability of being smaller is exactly p. If I have this quantile function, the Lorenz curve is the integral between 0 and p of the quantile function divided by the mean of the random variable. If I have f, I can compute these. And that is to say, I can have this curve. The Lorenz curve, here Max Otto Lorenz, has a certain number of very good properties. It is non-decreasing, so it increases in p, and p is between 0 and 1. It is convex, by definition, because the Lorenz curve always lies in this triangle, okay? So this is the limit situation from below, this is the limit situation from above, and we agree that this is convex, we agree that a line is convex. A line is also concave, but we just take it as convex. And it's non-decreasing, and between these two is convex. It is equal to 0 in 0. It is equal to 1 in 1. It has a very nice property of characterizing a distribution. If I choose a given f, to that f will correspond a specific Lorenz curve. And if I have a Lorenz curve, I can always come back to the original f. So I can always characterize the distribution. And this is something that later will be interesting. Is not very known, but it's quite trivial if you think about that, is that the Lorenz itself is a CDF. Because it's a quantity that is equal to 0 in 0, 1 in 1, non-decreasing, which are the requirements for a CDF. So the Lorenz curve is associated to a random variable that generates a CDF to which we associate the Lorenz curve, but you can always think of the Lorenz curve as the CDF of another random variable. That is not x, is another random variable. But still, it means that the Lorenz curve itself can be seen as an object that expresses probabilities. Okay. Now, since you are very, very clever students, you should already see something. I have introduced distortion functions. I have introduced the Lorenz curve. And these are completely different objects in the sense that distortion functions were developed by actuarial mathematicians and the Lorenz curve by statisticians working in the inequality study. But both curves are 0 in 0, 1 in 1, non-decreasing. So every Lorenz curve is a distortion function. By definition, is 0 in 0 is in 0, 1 is, when in 1 it is 1, and is non-decreasing. That was exactly what we were asking as properties of a distortion function. Then the Lorenz curve has more properties, like it is convex. But it is not a problem in the sense of being just a distortion function. Okay, so every Lorenz curve is the distortion function. Keep that in mind. It's a convex distortion function. So in principle, it does not generate coherent risk measures. The Gini index. I told you that the Gini index is twice this area. If you want to define that properly, it's exactly that. So you take the norm, the P1 norm of LP, your Lorenz curve, the perfect equality over the total area here. Okay? That's exactly the definition. And sorry. That's exactly the definition. In reality, there are many other definitions that can be used. For what I know, and if you want to be conservative, there are at least 14 different ways, and they are all equivalent, to express the Gini index. And that's the power of these kind of things. You can always find a proper definition that is suitable for you. For us, this is more than sufficient in this talk. Okay? So the Gini index is the area. And I repeat, when it is 0, it means that this curve coincides with the perfect equality. When it is 1, this curve coincides with the perfect inequality. If you want to see a couple of examples, let's take two very famous distributions, for example, in the study of inequality, but also in risk management and in financial mathematics, the Pareto distribution and the log-normal distribution. Now, the Pareto distribution is the prototype of a fat-tailed distribution. Actually, if you want to be very precise, every fat-tailed distribution is defined as some sort of distortion of a Pareto distribution. The log-normal is the distribution such that the log of the variable is normally distributed. So it's an exponentiation of the normal distribution. This is the probability density function for the Pareto. This is the probability density function for the log-normal. This is the Lorenz curve of a Pareto. So if I see these, I immediately know that this is a Pareto. This is the Lorenz curve of log-normal. What is capital phi? Capital phi is the CDF, so the distribution function of a standard normal. That is to say, a normal with mean 0 and standard deviation 1. And phi to the minus 1 is the quantile function of a standard normal. So what you have is that this is the Lorenz curve of a log-normal. The Gini, that you can compute as that area that we saw before, in the case of the Pareto is very simple. It's 1 over 2 times alpha, the shape parameter of the Pareto minus 1. And in the case of the log-normal is 2 times the CDF of the normal computed in sigma, the scale parameter, over square root of 2 minus 1. These are the two functional form for the Gini. The log-normal distribution has, for example, very nice properties. it's a Lorenz curve which is symmetric with respect to the anti-diagonal. That is to say, if this is the Lorenz curve of a log normal, and I take this diagonal, so the anti-diagonal, then it is symmetric. So all Lorenz curve of a log normal are, we say, self-symmetric. It's not the only distribution, but let's say it's the most important distribution with that property. So distribution whose Lorenz curve is self-symmetric. If you have another interesting properties on the contrary of the Pareto distribution is, for example, that for different alphas, the Pareto Lorenz curves will never cross. So you can order them. So you can also build statistical tests to check for the Paretianity of a given random variable. But these are details we don't enter into. Is not essential for the rest of the talk, but obviously this talk is very basic and I'm just giving you a flavor of these kind of things. I told you before that since the Lorenz curve is convex, I cannot generate coherent risk measures. In reality, there is immediately a way of bypassing the problem. The simplest one is to take the inverse of the Lorenz curve. If I have a Lorenz curve here and I take the inverse, I'm just taking the mirrored version with respect to the diagonal. By definition, it will be concave, so it can generate coherent risk measures. And if you want, there is also another representation, which is 1 minus a Lorenz curve computed at 1 minus p. That it has another name in the literature, which is called Lime-Kühler curve. But still, once you have a Lorenz curve, you can essentially find the concave version. This is very simple. Why? Because we know that the Lorenz curve grows like that in P. If I take 1 minus P, instead of growing like that, it will decrease like this. And then I take 1 minus, so it will be that. Okay? This curve is quite useful if you want to generate coherent risk measures. Okay, we have seen the distortion function, we have seen the Lorenz curve, and we have seen that the Lorenz curve is a distortion function. We can think of the Lorenz curve if we forget for a second about the socio-economical interpretation, and we just look at that as a mathematical object, it's a distortion function. Okay, so let's see 3 different applications of this. The first one is something that I'm pretty sure you know. It's the PQ change of measure. You know that when we price assets, so in option pricing, for example, we have risk-neutral pricing. So we have a measure P, which is the market measure or the physical measure. And since this measure P depends very often on the expectations of the different players on the market, on their different expectations on the drift of a given asset. They can also differ because of whatever other type of reason. We have to find a benchmark, which is the same and okay for everyone. And this benchmark is the risk-neutral pricing. So we get rid of the different idiosyncratic parts of the different expectations, and we create a benchmark, the risk-neutral pricing, by substituting the drift, mu, typically called, with the risk-free rate, r. Okay? Now, what I want to show you is we know that in the literature we have P, we introduce the Radon-Nikodym derivative, and we can switch from P to Q. But what I want to show you is essentially a Lorenz transformation. So there is a Lorenz curve doing something for us. Okay? And it's the following. Now, imagine that we are in the very, very basic framework. So I'm not thinking about fancy Levy processes, nothing. Very, very basic. Geometric random motion. Okay? My price follows a geometric random motion. If the price follows geometric random motion, and I have a capital T that represents maturity, and I want to know what will be the distribution of the log prices at maturity, I know that these are normally distributed, okay? And I know exactly the parameters. The mean is this object here. So if I think that S0 is the value of the prices at time 0, is log of S0 plus mu minus 1 over 2 sigma squared times t. That's the mean. The standard deviation is sigma, the square root of t. Okay? This is what happens under the physical measure, the market measure. What happens under the risk-neutral measure? If I introduce the change of measure, what I will have is that log prices will be still normally distributed with the same standard deviation, sigma square root of t, but I substitute mu with r. Okay? So you agree with me that these two normal distributions are essentially the same normal distribution, like that, shifted because of the mu r substitution. Okay? So if you want, we are exactly in this framework here. So this is my line. I have the first normal distribution that is centered, let's say, in R, because we assume that R is smaller. And exactly the same distribution, which is centered in mu. But the standard deviation here is exactly the same. It does not change. Huh? Okay, I have that. Now, you agree with me that unless I assume that mu is equal to R, if I take the ratio, for example, of the probability to be in the money or at the money, so that my price is above the strike price, this ratio will never be 1. Trivially, if R and mu are the same, these are the same object. So this is exactly the same stuff. So one divided by the other would be 1. But if these two probabilities are not the same, because mu and R are different, then the ratio will not be 1. Can be bigger than 1, smaller than 1, depending on mu and R. Okay? Now, if you take this and this, it's a very nice exercise that I really suggest you to try, because it's very nice to understand what is happening. And it's the following. You have P. You know that this is a normal distribution with this mean. The standard deviation is the same, so you don't need to change it. It's exactly the same. But you have this mean and this mean. And you want to see how you can move from one to the other. You can essentially prove the following. The probability under Q to be in or at the money, from now on I just say in the money, okay? So the probability to be in the money under Q is what? Is phi to the minus 1, the probability of being in the money under P, shifted by a quantity. This quantity, do you recognize anything here? Sharp ratio is exactly the Sharp ratio. So it's mu minus r over sigma is the Sharp ratio, and then multiply by the square root of time. Now, this is a probability. It's between 0 and 1. This is a fixed number, because these quantities are all known when I set my problem. So mu, r, sigma, t, they are known. So I can call this guy here C is a constant. This is known in the actuarial mathematics as the Wang transform. But the first time I saw it was, why do you need to call it Wang transform? This is the Lorenz curve of a log normal. You remember? This is exactly the Lorenz curve generated by a log normal. So, in the actuarial mathematics literature, is also known as the Wang transform. So this is the Lorenz curve of a log normal. And the question that we can ask ourselves is, okay, I know that this Lorenz curve is generated by a log normal random variable. what's the log-normal random variable that generates it. So I know that's the Lorenz curve, and from the Lorenz curve I can try to make inference about the random variable that generates the distribution that generates the Lorenz curve. Now, there I recognize the Lorenz curve as a log-normal Lorenz curve, so I know that the distribution is a log-normal. And now my question is, what's the random variable that is log-normally distributed? It's a random variable that we know. And that random variable is what? Exactly the Radon-Nikodym derivative that links P and Q. Why is it log-normal? Because this is the Radon-Nikodym derivative. It's the exponential of lambda, the Brownian motion in capital T, minus 1 over 2 lambda squared T. Now, this is a constant term. This is the Brownian motion in T. And what's the distribution of the Brownian motion? Normal. So if I take the exponential of a normal, it's log-normal. Okay? So that's my Radon-Nikodym. It's exactly the Radon-Nikodym that we use to change from P to Q. And if you want to move from Q to P, it's 1 over that object. Okay. And by the way, if Z is log-normally distributed, 1 over X, or 1 over Z, is log-normally distributed. It's a property of the log-normal. Okay, lambda here, just to summarize, is exactly the Sharpe ratio. Okay, I call it lambda just to simplify. If I know that this is my random variable and it's log-normal, I immediately know what's the Gini. The Gini is this. Is 2 times the CDF of a standard normal evaluating in lambda square root of T over 2. Minus 1. Okay. But then we have immediately a very nice brand new interpretation of the Gini index, which is no longer measuring inequality, but is measuring the distance, the distortion, since the distortion is given by the Lorenz curve, between the measure P and the measure Q. Why and how? This is my Gini. If Gini is equal to 0, it means that there is no distortion. It means that P and Q are exactly the same. And why is the Gini equal to 0? Because, for example, mu is equal to R. If mu is equal to R, lambda is 0, because lambda is mu minus R over sigma. So if this is the case, we know from the very beginning that there is not even the need of moving from P to Q. There is no distortion. But there is another interesting situation in which actually the Gini can be 0. And it's when lambda is 0 for another reason. Lambda is mu minus R divided by sigma. What happens if sigma goes to infinity? The ratio tends towards 0. And what does it mean? It means that in this framework here, we are flattening the normal distribution. So it's no longer this nice bell-shaped distribution, but it's something of this type. It's very, very flat. And if it's very, very flat, it becomes very, very difficult to distinguish them, because they will intersect for a great deal. And if sigma becomes plus infinity, they will essentially collapse over the entire line. So you will never be able to distinguish them. The opposite situation is when the Gini index tends to 1. And there are many situations in which that can happen. It can happen because the distance between mu and R tends to infinity, so there is a very big difference between the risk-free rate and the drift. Because time goes to plus infinity, and that makes sense, because obviously the longer the time horizon, the more the uncertainty, and essentially you are spreading the variance, or the volatility. Remember that volatility is sigma square root of T, so if T grows, obviously the volatility increases of your normal distribution, but also if, and this is funny, if the volatility tends to 0. Now, in certain situations, if you are a risk manager, it's not a big problem for you if the volatility is low. Actually, it's something that you like. But if the volatility is too low, what happens? It happens that these two distributions start to really separate because they are fixed on their means, but the standard deviations are becoming smaller and smaller and smaller and smaller. From a statistical point of view, the type of error that you can have in choosing one or the other increases. So it's a nice interpretation. When Gini tends to 1, what you have is that P and Q are by definition still equivalent, so they still agree on what is possible and what is not, but maximally distorted. What does it mean? For what is possible, they can assign very different probabilities. Okay? So if it's not possible that tomorrow something happens, they will all assign probability 0 to that. But if something can happen, according to P, it can be 20%, and according to Q, it can be 99.9%. Okay?
In the result that when t goes to infinity, the two measures collapse, what do I see here?
So when t goes to infinity, what happens is that this guy here tends to infinity. So this guy here is 1. So it's 2 times 1 minus 1, the Gini is 1. So it means that you have these, and since the standard deviation of your normal random variable...
What we find in the Hansen-Scheitman composition, in Hansen-Scheitman we should have that the distribution goes to 0 and the two measures coincide, so it's strange.
But actually it's not strange, because you have your two normal distribution and you're taking the normal to essentially become a degenerate distribution on the line, and then it's difficult to distinguish them.
Consider the class of people who are risk seekers, the mu can be less than r. In that case, your C would be less than 0?
Yes, in that case what you have is that it's no longer a Lorenz curve, because in order to be a Lorenz curve, C needs to be positive. If C becomes negative, you have minus C, it's plus C. It's minus minus C becomes plus C, and then it's concave. It becomes a Lime-Kuhler curve, if you want. But it still makes sense. So the point is that if you use this setting that I showed you, the curve that distorts P into Q is a Lorenz curve. And the curve that distorts Q into P is the concave version. If you enter in your setting, it will be the opposite. The curve that distorts P into Q, it's concave, and the curve that distorts Q into P is convex. Okay. This is the graphical intuition of what is happening. Now, this is our square as before. This is the CDF of one of the two normals under P. This is the CDF of the other normal under Q. And essentially for every single quantile here, we are looking at the probabilities and we are plotting them together. Okay? If you do that for all the different quantiles, you will get all the different probability, and this is exactly the curve that collects them, and that's the Lorenz curve. And the Gini will tell you how this curve is far from this, which is the ideal situation in which the two probabilities will always be the same for the different quantiles. Can you generalize the result? Obviously, yes. So I showed you the very basic geometric Brownian motion, but if I take, for example, a Brownian motion with deterministic drift and deterministic standard deviation or volatility, it works. Obviously, the quantity here is a little bit more involved, but you can work it out. Until you have some sort of path independence, you can work it out. When there is path dependence, it's a little more trickier. Okay, another type of distortion. Let's consider the European call. Works the same for the European put, for example. Now, you know better than me that this is the value of the call. Okay? I think that you know what these and these objects are. Okay, this is D1, D2, okay? But what's this? So what's phi, capital phi of D1? It's a probability. And what is capital phi of D2? It's a probability. But do you know what these probabilities are? So in particular, phi of D2, do you know what is that? Exactly. So it's the probability to be in the money under the risk neutral measure. And what's this? It's again the probability to be in the money under another measure, which is not the physical one. It's the share measure. That is to say, the measure which is equivalent to P, which is equivalent to Q, in which the numeraire is not the risk-free asset, but is the stock itself. Okay. You can express the Q as a function of D, and it's again a log-normal Lorenz curve. You can express the D as a function of, there is a typo here, so it's not, obviously, this is D as a function of Q here, so this is a Q. And what happens? In that case, it's not a Lorenz curve in the proper sense, because it's plus this. This is positive by definition, because it's a standard deviation times a time component. So this function is concave. But it's reversed Lorenz, Lime-Kuller, as you want to call it. We can still play with that. But for a guy just in inequality studies, it's no longer formally a Lorenz curve. But if you ignore the inequality, meaning it's a mathematical objects with very nice properties. Okay, the last example, and then if you have questions, is the following. I don't enter in the details because we don't have the time, but I think it's very interesting. We deal with extremes, so very large objects, maxima or minima. So imagine that you are interested, you are a credit risk manager, and you are interested in modeling joint defaults in your portfolio. Not just in the default of one counterparty, but in the defaults of several counterparties at the same time. Because what you are most scared of is the fact that many guys default altogether, okay? And you don't have the money to cover for that event. Or, if you are a little bit familiar with the Basel framework, there is another situation in which you can be interested in the large co-movements of two quantities. And it's when you are interested in modeling the joint behavior of the PD, the probability of default, and the LGD, the loss given default. The probability of default is just the probability that your counterparty goes default. The LGD is the percentage loss that you have in case of default, as a percentage of the exposure, okay? So if I'm a bank and you are my clients, each one of you will have, say, a mortgage with me. The mortgage has a given nominal value, the exposure. If one of you defaults, I risk not to get my money back. But since most of the time there is a collateral that I can sell and stuff like that, I will never lose the entire amount, the entire exposure, but just a percentage of that. That percentage is the loss given default. Okay. This is the typical, okay, I drew this plot, so it's not obviously corresponding to any particular data set, but if for the different clients you may have, and that have defaulted, and that have generated a loss, you plot the different probability of default before defaulting and the loss given default, so what they actually lost, you will find a plot like that. So all quantities are between 0 and 1 by definition, because one is a probability and the other one is a percentage, so between 0 and 1. And you will always observe that here, in the upper part of the square, there are a lot of dots altogether. Because when bad things happen, they tend to happen together, unfortunately for us. This is what in risk management is called wrong way risk. Not only the probability of default increases for a counterparty, but also the loss that you can expect from that counterparty increases. Okay, There are different ways in which you can try to model this object. A very common one, and here we have an expert in that, which is Professor Cherubini, is copulas. You probably heard of copulas, okay? Copulas are a way of representing the joint distribution of several random variables, okay? You use the Sklar theorem, you know that you can transform the marginals into uniforms using the probability integral transform, and then you find a function, the copula itself, that links these marginals. Now, within extreme value theory, there is a specific group of copulas. Again, I will not enter into details, but believe me, they are called extremal copulas or extreme value copulas. And they are all the copulas that I can represent in this way. So the copula between U and V that are already the uniform marginals is equal to U times V, which is nothing more than the special case of independence, okay? Because I know that if two random variables are independent, if I take the joint distribution, it's just the product of the marginals. This thing remains true even if I move to the uniform margins, okay? So that will be just the product of the two taken to a given exponent. This exponent is a function, p, whose argument is this strange ratio of the log of u divided by the product of the logs. The log of the products, sorry, the sum of the logs. Now that argument there is called, if you want, you call it t, and extremal copulas are extremal copulas only if they admit that representation. That function here is known as the Pickens function, and is a very special function that maps from 0, 1 to 1/2 1, and is bounded by two quantity, 1 minus t and t. So your Pickens function will always lie in this triangle here. It's a function that is 1 here, 1 here, and convex. The limiting situations are equal to 1 for all values of the argument, equal to 1 minus t, and equal to t. These three possibilities are easily understood here. Assume that this is always equal to 1. What happens? You are just in the case of independence, because it's u times v to the power of 1, which is u times v. If, on the contrary, it is equal to t or 1 minus t, perform the substitution, and you will find that the result will be either u or v. So you essentially are in the situation in which the two random variables are comonotonic. It means that one is just a transformation of the other, okay? So they are maximally dependent. Okay, without entering into the details, my suggestion is to think about this plot and start thinking what can happen if I take this triangle, I rotate it, and I inflate it so that I get a Lorenz curve. This function here is 1, 1 convex. If I rotate the triangle, taking this as a pivot, and I inflate it, this point here will go to 0. This point here remains in 1, and this is still convex. It's a Lorenz curve. Why is it useful to do that? Because doing this very silly trick solves one of the problems of the Pickens function, which is the fact that there are not many parametric forms for the Pickens function. But if this is the case, and you know how to move from the Pickens to the Lorenz and from the Lorenz to the Pickens, since we have hundreds of Lorenz curves, we can generate Pickens functions. And even better, from a probabilistic point of view, you can characterize the probability generating measure of the Pickens function. This is technical, so ignore that. And it's very simple to estimate, because we have a lot of knowledge on how to estimate the Lorenz curve. There are many other distortions that I don't cover in this talk. Think of any pricing formula of the basic ones. If you invent a new very cool and fancy option, I'm not sure, but if you think of the basic ones, they are essentially always, there are always Lorenz curves intervening. If you take copulas, the Archimedean copulas can be characterized by a specific function, which is called the Kendall function. It's a concave function, 0 in 0, 1 in 1. The Kendall function can always be seen as the inverse of a Lorenz. With Lorenz curves, you can generate copulas themselves. This is a paper I recently published. If you think of model risk, it's again a Lorenz curve. Have you ever heard of the area under the curve as a measure to compare models? Okay, if you know that, it's a concave function that goes like that. 0 in 0, 1 in 1, concave is the inverse of a Lorenz curve. Okay, so just to let you know that there are many possible applications, and given the nice properties of this object, if you recognize it somewhere, it can be extremely helpful in solving your problem. Okay, thank you very much.